So, welcome everyone to the fourth class of the problem and solving series for the course of chemistry and physics of surface and interfaces. Right. So previously we have done three sessions where I have discussed the weekly topics a bit, and then mainly solve the assignments that is provided by the fellow faculty, provided by the faculty members or the TA or the course, right? So today is the fourth class, and in this in today's lecture, I will try to solve the assignment 4, right? So before going to that, I'll try to tell us like what are the topics covered. We'll discuss a very bit, like I'll just point it out the topics that are covered in this week, and then go one by one question each, right? So first of all, in this week, we have learned about molecular adsorption, right? So we have known a very detailed discussion about molecular adsorption, how it is, like what are the energetics, what are the forces that are going to control the Adler symmetry. Like previous week, we have learned about the in the previous week we have learned about the atomic, right, atomic adsorption. If the Adler atom, like Adler moieties are atoms, in that case we have already thoroughly discussed. And in this week, mainly we have learned about molecular adsorption, and the and a thorough discussion on that. And second, so welcome to the class. So what I have stopped telling, what are the topics covered in this week, right? So the topics are, first of all, we have learned about the molecular adsorption and details of it, and second of all, that is just introduced in this week, that is scanning tunneling microscope. And this week assignments questions, that is the assignment number 4, are mainly based on this. Like all the questions are from these two topics. So with further ado, let's start the questions, each questions one by one. So this is the first question. What it is written, which of the following is not correct, right? Not correct for STM or scanning tunneling microscope. So, in the last of the today's discussion, I'll try to tell a very brief about STM because that is also introduced in this week. So before like that will be the last thing I'll do. So let's face this question. What it is written, like which of the following is not correct. So first option is STM is widely used in both industrial and fundamental research to obtain atomic scale images of metal surfaces. Obviously, it is true. Like the purpose of STM is actually to get a atomic level, like atomic resolution micrograph, right? And that is what made this technique so special, so that it can earn a Nobel immediately after discovering. And it is like this is a very common thing. Like it is actually used in both for research as well as an industrial research as well. And then only electrically conducting samples can be imaged by an STM. So what we have seen, so in case of STM, let's say this is a surface which is having like surface molecule somehow arranged, and let's say there are some add atoms are there. Now, in case of STM, there is an atomically sharp tip, very sharp tip, and it scan one by like in some in this two direction, and then try to tell like the height. Let's say if this is surface atom, this is a less height thing, and air atom is above that. So the height of this tip, like if we keep the tip at the same height, let's say this is the height I am keeping in the tip. So the distance between this to the surface molecule will be somehow different than the distance between this and the ad layer. and that will tell us the current, like that will change into the tunneling current. I'll discuss that about in detail. I'll try to do that. So that the basic thing is we are measuring the tunneling current depending upon the height, right? So that means this tunneling current, that means the electron is actually tunneling through this. So it should be a electrically conducting samples. That is the that is a thing you need to know for scanning tunneling microscope. And normally by scanning tunneling microscope, one can uh, like get the topograph of metals, semiconductors, mainly these two, and very thin film of like insulator can also be done. But normally insulators cannot be done by STM. Right. So let me take you. Someone is joining. Yeah. So that means this needs to be electrically conducting, and so that means if we go to the third option, can also analyze insulator. That is not true, because we are maintaining some voltage. We are measuring the current, right? Between each of the atoms, how different it is, and that's why we are converting it to get the topograph. So that means insulator samples cannot be done, and that is like what is asked, which is not correct. So these two and three option, these are contradictory. Like if it is true, then it is not. So obviously we know that is electrically conducting samples can be imaged. That means this is not correct, and this is your answer. And also the fourth option, let me read out. Tunneling current is strongly dependent on the distance between tip and sample. Yes, that is what the principle is. Like whatever the distance is, like this is a, let's say, tip, and this is a surface molecule. Now if it the second, this is a first surface molecule, let's say, and this is a second, and this is the, let's say, third. So depending upon distance between these two, we are going to get the topograph. So that, and we are practically measuring nothing but the tunneling current. So the tunneling current is strongly dependent on the distance between tip and sample. That we already know. So all these three options are correct, but not this, right? So this is our answer. Okay, let's go to the second question. So what is the question? Let me read out it first. The question is, which of the following statement is a correct regarding molecular ad layer? So I already said in this week mainly two things we have learned: a detail about molecular ad layer, and then molecular adsorption, and also the upbeat introduction about the scanning tunneling microscope. So what is a molecular ad layer? So let me just first read out the options, and then I'll try to explain what will be the answer and how you can reach up to that. So on increasing the thickness of the molecular ad layer leads to change in the molecular orientation. This is the first option they are saying. At the interface, there is large influence of surface. Therefore, the molecule surface interaction prevails at that point. Ad layer pattern of a thin film is dependent on the ad layer coverage, and all of the above. So, like in case of atomic ad layer or atomic ad layer formation, we have we know we have two options, like, right, that is two forces that are actually controlling this: intramolecular force, and another is inter. What is inter? That is between, sorry, add atoms add atoms interaction, and inter is add atoms with the surface atoms. So these are the two main forces. And in case of molecular adsorption as well, these two are the main forces. But in case of atomic adsorption, these two intra and inter are not that much complex. Like this is only the interaction between two atoms, and the interaction between surface and the atoms. That is the intermolecular interaction, and this is the intra. But in case of molecular, the main two components are these two, intra and inter. But this intra it depends upon the molecular orientation. That means if you go through the lectures, you will get to know about some azimuthal angle. So how these molecules are actually uh, like oriented in the surface, that depends, like that is very very important to know about the intramolecular interaction. And that's why if it is, let's say, energy, let's say this is the intra energy I'm talking about, and this is case for the atomic, sorry, let's say this is the case for, this is the case for atomic. In case of molecular, there will be very very various minima before. So there will be some local minima, local energy minima, because of some because of the arrangement. So it can be somewhat different arrangement can be possible, and due to that, there will be many more minimals, many more energy minimals. So that will not be simple, but the main two part are these two, intra and inter. Now, if we think this is a surface, and now one by one atoms are coming. Let's say this is some molecules, add molecules I'm talking about. Then above that some second layer is forming and all. So obviously in this layer, the first layer, that add molecule and surface interaction will be higher, and whenever you go to the top, that time the influence of surface is going to decrease, right? That is, that are the some things about the molecular idea. So this is, try to look at the graph. So this is the graph. Like this is for E total, that are depending on. So I think you are, it is visible. So E total is mainly the contribution from two part, E intra and E inter. So this is the daily intra and this is the daily inter for for atomic. But in case of molecular level, there will be various minimas, and this is also not, will not be very straightforward. This will be, there will be obviously periodicity, but there will also be various minima, because this is not straightforward. There are very like various kind of interactions are taking place, various different things you need to think of. So, on increasing the thickness of the molecular ad layer, so that means we are going, like thickness means the ad layer thickness is increasing, means more and more ad molecules are actually depositing. So then now there will be a very less influence of the surface whenever the thickness is higher. That time the influence of surface will be much less. So that time surface is not going to determine the molecular orientation, right? So in case of this layer, let's say first layer, there will be a high influence of the surface, so that how that molecule is actually depositing. So let's say like the surface and molecule, surface molecule and then add molecules are trying to interact in a manner, like trying to orient themselves in a manner in which orientation they will have the more interaction. But whenever we go to the top, that times as the thickness increases, the surface influence will be lesser. So the molecule will try to behave in a, like in a manner how it will behave in the bulk. So obviously molecular orientation is going to change. Let's say a molecular bulk, like crystal orientation of a bulk, a molecular bulk crystal orientation is, let's say, linear, and the surface is a cubic. So it will, in the first layer, it will try to have some more orientation, and due to which it will have the more interaction with the cubic surface. But after that, it will try to behave linearly. So this option is obviously correct, because the surface interaction is actually decreasing with increasing the thickness. So obviously, the molecular orientation is going to be uh, more and more like bulk if the thickness increases. And now at the interface, there is large influence of surface. Obviously, that means the surface interaction. That is what I have said. So this is also true. Now, ad layer pattern of a thin film is dependent on the ad layer coverage. So that is also we have seen in the atomic adsorption case as well. So that depending upon the coverage, now the island formation or the growth layer to layer growth formation are actually happening. So that is also true. So that means what will be the answer? This will be all of the above, right? I think you understood this thing. Okay, let me go to the next question. So this is the answer. So I was talking about the orientation, right? So these are the orientation. Let's say, let's say this is my molecular state. So this is my molecule. It can arrange like this, and also it can arrange like this, so that it can be like this, and also it can be like a bit. Let's say this. So the add molecule lattice can be like this kind of. And you can see clearly the interaction will be much higher in this case. So depending on the molecular orientation, my my interaction energy intra is going to be different. That is what I meant while talking about this. Okay, so go to the next question. I think you have understood this. Okay. So what is the third question? Solvent used in the study of solid liquid interface should have. So this is actually you can find it from in lecture number 19. So there, professor has actually discussed about solid liquid interface a bit. And in case of the solid liquid interface, mainly the solvent is actually playing like the solvent is playing a very crucial role, right? And that solvent needs to have low dielectric constant and low vapor pressure. And normally in this course, we will use fatty acids and fatty alcohols or phenyl octane to get solid liquid interface, right? And why these are important, you will come to know in the next weeks and onwards. Whenever there will be a very long discussion about the scanning tunneling microscope, and then solid liquid interface will automatically come, and then you can understand. But it is introduced like low dielectric constant and low vapor pressure is actually very important. And also, let me tell you that the nature of the fatty acid and in general nature of the solvent, like the chain length of that solvent and all actually going to play a very important role about the add layer pattern, molecular add layer pattern, or solid liquid interface, how it will look like. So here it is given should have high dielectric constant. That is obviously not true because we need low dielectric constant, and it is written high vapor pressure, and that is also going to be incorrect because we need low vapor pressure. And the acid and fatty alcohol, this is fatty acid and fatty alcohol, these are mainly used. So this is going to be the answer. All of the above is, there is no question of having this answer. So this is the answer. So this what is the answer? Solvent used in the study of solid liquid interface is mainly fatty acid and fatty alcohol that are used as a solvent, right? So in every slide I have given the answer in the like the bottom of the slide, right? You can find it. So go to the fourth question. Tip surface separation in STM is in the order of few. Okay. So now let's discuss about the STM first because we'll be having STM questions, many more STM questions. So I'll discuss here what is the scanning tunneling microscope and all. Let me just check if somebody tried to join here. Okay. Yeah. So this is a basic diagram of uh, scanning tunneling microscope. Normally, very atomically sharp tip is required, and voltage between this tip and the sample is actually maintained. That is called the set to maintain the set current. There's a this voltage is actually maintained, and this tip can be scanned in both all the direction like x, y, and z. Now the direction of z, like the z direction, is not actually independent, because let's say this is a surface, this is surface, and this is very corrugated surface. Okay, let's say this is like this. So now, if we like fixed, sorry, if we let's say fix the tip, let's say this is the tip. If we fix the tip, so here it is okay, we can measure the tunneling current. But whenever it will come here, it will actually like break. It will try to break, or it will get a like obstacle. So to do not like, it should not be the case, right? So it will actually rupture the surface, or it will destruct the surface. So that's why tips need to change according to the tips need to change the height. This tip needs to change the height according to the surface corrugation or surface structure, and that is what maintained by the feedback amplifier. There's a feedback loop which is actually constantly measuring the tunneling current, and whenever like in this case there will be very high tunneling current, at that time the tip will try to adjust the height and then maintain the same voltage. Okay, so let's say it is like this. Now some molecule comes, so it will again go back to this. Again, some there is this molecule is there, it will again come back. So like that, the height of the tip is always going to be adjusted following the feedback loop. So this is the basic thing of Z direction scanning, and X and Y are independent. It can move like in here and there. Like okay, so in every position Z is actually going through the feedback amplifier, that is dependent, and X Y are the independent. Now the scanning tunneling microscope is actually following to know understand scanning tunneling microscope. We need to know three things, three effect. One is quantum mechanical effect of tunneling. Let me change the color, tunneling, and another thing is piezoelectric effect, because this tip, like we need to move this tip because we want to get a atomic resolution of the topograph. Atomic resolution we want na. So that means this this movement of this piezo scanner needs to be very precise, and one simple mechanical devices cannot do that. So we need some very sophisticated technique, and that is the piezo scanner. So that is depending upon the piezoelectric effect. So that's why we need to know what is piezoelectric effect, and lastly a feedback loop. That is what we have talked about. So mainly three basic effect is actually used here. That some first of all, main thing that is in the name as well, that is tunneling. So the quantum mechanical effect of tunneling, then piezoelectric effect, and feedback loop. So, what is piezoelectric effect? First of all, the piezoelectric effect was discovered by Pierre Curie in 1880. The effect is created by squeezing the sides of a certain crystal, such as quartz or barium titanate. The result is the creation of opposite charges on the sides. That means if we that crystal is now going to give a feedback, like going to behave according to the voltages applied on the crystal. Okay, so depending upon the voltages, it will elongate or compress. So the elongation or compress is in the atomic resolution, and by that we can actually raster the surface and get that. Okay, okay. So that this materials are used to scan the tip in scanning tunneling microscope, and most other scanning probe, scanning probe techniques that are discussed in the very introduction of the lecture of scanning tunneling microscope. Any kind of technique is actually require a tip or something like that. So that is actually always is normally is a piezoelectric material. Normally a piezoelectric material, that is lead zirconium is also of example, is actually used in scanning probe microscope. So this is piezoelectric. So depending upon the applying voltage, the material is actually behaving like that depending upon the voltage applied. Now, what is quantum mechanical tunneling? That is, we already know in our BSc level or like graduate honors level um, quantum mechanics. So, what is tunneling? Tunneling is like where a molecule does not have any probability to go classically, but still it can go due to the wave nature of that particle, right? So let's say electron. So and I am putting a barrier. This is my barrier. This is also barrier. This is a barrier. So I'm putting a barrier with high potential, let's say. should not go because electron doesn't have that much potential to overcome this barrier. But still, due to the wave nature, wave function directly does not stop at the boundary, so it go beyond something that. Now, if the thickness of that barrier is that much higher, so that it like dies out before coming out that thickness, so that time we cannot get any probability of electron here. Here we will not get any probability after that barrier. But if it is not that much thicker, then we can get probability of electron or probability of that material which is tunneling through somehow here. Obviously, uh, as this press is not classically like the probability is very less, we are not going to get very much electrons, right? And then this number of electron is also depending upon that barrier thickness, right? That is like depending upon the barrier thickness, we are going to get, sorry, we are going to get how many electron numbers we are going to get. That is dependent upon the barrier thickness. So number of electrons that will actually tunnel is very dependent upon the thickness of the barrier. That is what I tried to understand, like make you understand. If the thickness is that higher, so electron cannot come out, even if the tunneling is occurring, because like tunneling also have some up to certain limit it can go beyond the classical limits. So if it is thinner, then only. And then, so that is what I've said. So this is current. That current through the barrier drops off exponentially with the barrier thickness. So this, the dependency of that thickness is not straightforward. It is an exponential dependency, right? Now in case of STM, so what is the tunneling probability? Because there is no contact between this tip and this surface, there is a gap, right? There is a gap, and this gap is normally in the nanometer order, some 1 or 2 few nanometers, right? So this gap, so there may be vacuum or air, or if in case of solid liquid, in case of solid liquid interface can be some liquid. So this is the place. So now electron is tunneling through this. So depending upon the barrier, we will get the tunneling current. Right? You understood? Okay. Now let me tell you about something we already discussed. That is a feedback loop. Feedback loop actually monitors the tunneling current and coordinates the current and the positioning of the tip, so that the tip doesn't destruct the itself does not get destructed or destruct the surface. We get the correct information about the surface. So a feedback loop constantly monitors the tunneling current and makes adjustment to the tip to maintain a constant tunneling current. So it is actually constant like always maintaining the constant tunneling current. So whenever it is coming like in this position, that time the tunneling current will be higher, so the tip will now adjust its distance. Whenever it is there, tunneling current will be somehow lesser, so tip will again come back into this direction, like that. So like that, so that less having a constant current, the tip is actually moving. So that's why if as we are always trying to take a constant current, so this kind of imaging is known as constant current image. Okay, always the current is actually same in the in the imaging technique. Now tip is adjusting itself through the feedback loop, feedback control, its height and maintaining that current, and we are getting the image similarly. Image that's how we are getting the image. So that is called as constant current. And there is also something called as constant height image, where like in case of a very flat surface, normally it is actually we normally do that. Tip is actually fixed at a height, then just where current is actually we are measuring the current. Okay, so how the current is changing, that is going to give us the surface. But in case of very corrugated surface, this cannot be done because of the thing I have said, that the tip is going to be destructed like that. So this, and whenever this is the height is actually fixed, that time it is called as constant height image, right? So these are the thing I want to discuss about STM. Now let's go back to the question, right? So that is the question. The tip surface separation in STM is in the order of few. We already seen this is nanometer, 1 or 2 nanometer. So we do not waste any time here. We already know about this STM operation, and normally the tip to surface distance is kept as few nanometer, right? Obviously, centimeter and picometer tunneling is not like one thing I need to tell you that why what is the surface separation we need to take, like what is the tip surface separation, that is depending upon the tunneling, right? What is tunneling? Classically impossible region that can be achieved only by the wave nature of the particle in case this is electron. So obviously it cannot be much higher, like it cannot be centimeter, it cannot be. This is totally wrong. Centimeter and micrometer are much larger scale. They are a tunneling is not possible, and normally it is kept at nanometer, right? Okay. So go to the next question. That is question number 5. On increasing the thickness of the molecular add layer on surface, the self-assembly is controlled mainly by. We already discussed. Let's again discuss this. So let's say this is the surface. So this is the surface. Okay. Let me change the color. And now a molecule. I like to say this kind of molecules are coming like that. So this is the surface. This is the surface, and then add atoms are coming. So if we think about this layer one, right? So this is layer one. I'm talking about. Here, the surface and add molecules interaction is there. That means the intermolecular interaction is there. And whenever we are going through this direction, the above and above layer, so that time the influence of the surface is decreasing. Now we know two type of interaction we are talking about always: intermolecular, that means surface and add atoms, and intra, that means add. Sorry, I'm always talking about add atoms. Here it is add molecules. Now add molecules. What is here? So this is intermolecular, that is between surface and add molecules, and this is intramolecular, that is add molecule. So here this molecule interaction, that is intramolecular interaction is also there, and intermolecular between the surface and molecules. Both are there, and whenever we are going like above and above layer of the surface from the surface, the influence of surface is actually decreasing, and like on increasing the thickness, basically there will be no molecular, like there will be no interaction from the surface. So mainly that will be controlled by the molecule interaction, right? Because molecule surface interaction is the when the thickness is very less that time. So there is no question of both A and B, and no question of none. So that is the answer. So this is the answer. Molecule interaction. Whenever the thickness is higher, we are going to get the adsorbent. So add a molecular layer, depending on mainly that is mainly controlled by the molecule interaction. So what is the question of 6? What are the factors that control the assembly in solid liquid interfaces? Right? We already said that solvent in case of solid liquid is very playing a very important role. Right? Solid and listen, before going into that uh, question, I want to tell you that the basic application where the solid liquid interface is actually coming. Solid liquid interfaces are occurring in many fields of technology, like if you think about catalysis, if you think about electrochemistry mainly. So in electrochemistry we normally take like the electrodes, right? electrolytic solution. So there is always a solid liquid interface, SL interface. So in energy materials, obviously, so in the all the very like important cases like biosensors or biological membranes, there is a, into the biological membranes, obviously there is a solid liquid interface. So the solid in study of solid liquid interface is very important, right? Now normally this is the main things that controls the solid liquid interface are the concentration of the solvent. I said the solvent is actually very important in case of solid liquid interface. So the concentration of the solvent, and we have seen in the lecture. So taking a solution, we are having the add molecules. Now just by sonication to some hours, the surface let's say these are the 3 hours. Let's say this is 0 hour, this is 2 hour, and this is 4 hour, and the surface geometry is actually changing, right? The surface geometry is actually changing. So that is also very so that means the constant concentration of solvent is very important. Now nature of the solvent we have already seen in the lectures, like the chain length of the solvent, right? If it is decanoic acid and it is butyric acid, the similar kind of molecule in the similar surface is going to give us a different kind of arrangement. So the nature of solvent in case of solid liquid interface is very important, and that is what is actually chain length of the solvent, and also the temperature, because in the last assignment also we have got a problem of KCP versus TCP, that is kinetically controlled product versus thermodynamically controlled product. So in normal temperature or low temperature, normally that product will be available which is having which is going through a like lesser amount of activation potential. And now if we increase the temperature, then it can have the ability to go through a higher activation energy, higher activation energy, because after that the product is actually much more stable. And we have given a beautiful example. You can go back to the assignment 3 discussion, and that is available in my YouTube channel, and as well that will be provided to you as well. So my YouTube channel name is Tanmay Khan, PMRF-IIT Kanpur. You can go through that. So there I have given the beautiful example of KCP versus TCP in case of surface, as well as in case of like basic organic chemistry also. That is very important. So I have discussed. So the temperature is also very important. So what it is written, the concentration of molecule, obviously that will be a case. Type of solvent, I already said, and the temperature. That means this is all of the above. So let's. I have given some the pictures taken from the lectures as well. So let's say this is. So this is a normal trimesic acid on the graphene surface. But it can have two different kind of structure. One is chicken wire structure and another is flower structure, depending upon the dimeric or trimeric hydrogen bond. Right? We can have both two. Just like we can have the different kind of structure. Now let me erase this so you will understand. You can see here the butyric acid, pentanoic acid, and hexanoic acid. Normally, when the chain length is small, that time we are getting flower-like structure. When the chain length, that is octanoic acid, heptanoic acid, nonanoic acid, chain length is higher chain length, we are getting chicken oil-like structure. So type of solvent is very important, right? Now let's say this is temperature. At 20 to 40 degree, the surface pattern is kind of like this, and whenever we increase the temperature, it goes towards like from chicken wire to flower with the temperature. So whenever you increase the temperature, it goes towards flower-like structure. So obviously temperature is going to play a very important role, and we already know that there will be a very uh, important example that is already given in the lecture as well. you can go to the lecture. It will be in probably in lecture 17 or 18. So by sonication as well, in this case only, one can go from chicken wire to like flour, or flour to chicken wire by sonication. Sonication is nothing but increasing the increasing the local concentration local concentration in the surface. So that means sonication can also give to that. That means concentration of solvent molecule is important. So this will be the answer. So all of the above, right? All of the above is the answer. Very simple. So go to the question number 7. This photo is actually taken from lectures, and it can be found in Chem Review by S.R. Forrest, 1997. It can be found there as well. So here, like the how the binding energy or the adsorption energy is changing from atom to molecules, like depending upon the diameter of molecule. The diameter is a bit difficult to understand, but you can think of like the area of contact or the contact position. Like if the molecule is like bigger, so that means the area of contact is going to be higher. So depending upon that diameter of the molecule, how the adsorption energy changes. Normally in case of atoms, normally bond forms, right? Bond forms. It may be covalent or ionic. So if a bond forms, energy is going to be much higher. And big molecules are, in case of big molecules, the strain actually increases, and there is very less chances of getting a bond. So it is mainly guided by a Phillips options type or the Van der Waals kind of interactions. So the energy is lesser. So whenever we go in that direction, energy normally decreases. So if it's an atom, then atom-like molecules, like atom normally stick like this. Let's say it's a small molecule like carbon dioxide. So it will be like this, similar kind of like molecule. Or let's say this is N2 molecule I'm talking about. That can also behave like a atom-like thing. So the energy is for some small molecule, atom-like molecules will be like much higher than the big molecules. So depending on the like molecular size, if it is higher, that time the energy is going to be lesser. So let's go by this. This is nitrogen, obviously then benzene, then thiocyanin, then copper atom. This is atom, right? So copper atom cannot be the lowest energy. It is going to have the highest. So this one is the answer. And thiocyanin is the most big molecule here. This is thiocyanin. So this is copper atom. Then nitrogen. This is atom-like molecule. Atom-like molecule. This is atom. This is small molecule, and this is big molecule. So in the total, the in case of atomic absorption, the energy is going to be the highest. So this is the answer. And that is this is very simple and very good question as actually. So from atom to small atoms, sorry, small atom-like molecules, then small molecules, then big molecules. This is the order, right? I hope there is no problem. Okay, let's go to the next question. Here we only need like two more questions to be discussed. Which among the following is the possible electrostatic interactions between molecule when they adsorb on a surface? So, in the very first beginning of the molecule interactions, it can be anything like electrostatic interaction, ionic interaction, ion dipole interaction, or hydrogen bond, cation pi interaction. These kind of interactions are possible. What is electrostatic interaction? Let's say a molecule is actually like electrolyte type kind of molecule. Let's say we are having an ionic bond. It can have directly ionic interaction, or ion dipole interactions. Normally, in supramolecular assembly formed between hydrogen bonding, like that case, we have seen this chicken oil like thing, this trimesic acid. This trimesic acid actually having dimeric hydrogen bonding or trimeric hydrogen bonding. Depending upon the hydrogen bonding, the arrangement, molecular arrangement of the add layer is actually changing. So that hydrogen bonding, also the pi interaction, like in case of let's say naphthalene, if it is interact, it has nothing to do but the pi electron. So depending on the pi interaction, also assembly can form, or that molecular adsorption can happen. So pi interaction is very important, and van der Waals interaction is a like ubiquitous in nature. So it is omnipresent. It is present everywhere. So so obviously there will be van der Waals interaction. And normally in case of van der Waals interaction, let's say uh, I have given this kind of molecule. So if it arranges like this, van der Waals is like the interaction. It is only interacting in this point and this point. And now if it is arranged like this, and let's say it is arranging like this, in this case, only these 2 point of interaction. Let's say I'm talking about one van der Waals. Here, 3, 4, the interaction is higher. Now, the interaction is like this, much higher. So, obviously, if the assembly, if the I'm talking about the assembly, if the assembly of molecules is governed by van der Waals only, let's say this is number 3, this is number 2, this is 1. So, only then 3 will be the case. This will be the this will be the arrangement. If it is only governed by the van der Waals, and that is what actually happens for the trimesic acid or the benzoic acid 1,3-mesobenzoic acid, like that. Sorry, uh, where there is no hydrogen bond, obviously. Sorry for my comments. Like when there is no nothing but the van der Waals interaction, that time the 3 is going to prevail. And such kind of examples are already given in the lectures, like in the actual lectures. So you can go through. Also, hydrophobic interaction, it is also somehow ubiquitous in nature. It is always there. Now, chelating effect, that is actually due to chelating, great amount of energy actually released. So the chillate effect can also can also tell about the can also tell how it is going to actually happen, right? How it is actually going to happen for the molecule interactions. And in each case, whenever it is monopole, dipole, it will depend upon the distance. And in this manner, in case of van der Waals interaction, it depends upon 1 by d to the power 6. In other case, it is like that. So you can go to the lectures and again recapitulate the things I'm saying here. So that means, so which among the following is a possible electrostatic interaction? The dipole will also be there, ionic interaction will also be there, and ion dipole. So the answer is nothing but all of the above, right? So that is all. That is also written here as well. So this is the question answer. Now I already talked about the scanning tunneling microscope, how it is actually happening, and that. So remember, the distance between this cannot be much higher, because this this is depending this process is dependent on the tunneling, and tunneling is not like it can be possible up to micrometer or millimeter like that. It is only possible in the nanometer picometer range. So that's why it is kept at this distance, right? I have talked about the feedback and all here, and discussed about these three things like quantum mechanical effect of tunneling, physioelectric effect, and feedback. How the feedback loop is actually happening. So now come to the question number 9. Which among the following factors control the resolution of imaging in scanning time tunneling microscope? Which among the following factors control the resolution of imaging in scanning tunneling microscope? So resolution mainly depends upon that while measuring the stability of instrument needs to be like very very high, because let's say there is your atom and there is your surface, and now this tip is constantly vibrating. So you cannot balance between this, like we are measuring the tunneling current, right? If it is constantly vibrating, the tunneling current can also be like will also be changed. So the picture we are going to get will be very very hazy. So that stability is very very required. The stability mainly is vibrational, like or electronic noise or normal acoustic. Sorry, this is acoustic, right? Acoustic. So while experiment, one should not talk loudly, and that normally the instrument is like kept in a damping table, like where the vibration, a small vibration cannot rotate, like cannot create noise in the experiment. So it is actually, if let's say this is the STM, it is kept above like 3 4 kind of damping tables, right? So that vibration normally don't disturb the experiment. Now, atomically flat surface, if it is there, so that time obviously, like if the surface is very very flat, not that much corrugated, so the measuring will be very very easier and the resolution will be higher, because tips need not to be changed and positioned, like need to change much, need not to be changed much, and like whenever a tip is actually changing that much, so there is actually a time you need to give to settle it down and all. So if it is very very flat, atomically flat, there is no also there is atomically flat means there is no kind of noise, like there is no impurity if it is not there. So that time also the signal to noise ratio of the images will be very very high. So this is actually true, we know already. Okay, so the atomically flat samples are actually higher resolution, I told you. Now radius of the probe. So because we are measuring in atomic level, so now if my probe is this big, if the radius of the probe is this big, or like I'm talking about T pad itself, right? This is the T, let's say. If this is bigger than my atom, then one cannot measure with this tip. We need to have very very flat tip, very very atomically sharp tip, so that the atom is actually like bigger than the tip size. So radius of the probe is very very important. We cannot use a higher radius, like bigger bigger probe, bigger tip. Also, if we keep the sample at low temperatures, there will be no contribution from the thermal modes. So that time also, and if you keep it in the ultra high vacuum, so that means there will be no impurity and all. So that times the resolution is much much higher. So obviously radius of the probe is going to determine the resolution, atomically flat surface, and stability of instrument during scanning. What I already discussed. So and also here is not written. Also the low temperature. If you keep it low, then high resolution picture can be obtained. So all of the above things are actually possible. Like actually can factors that control the resolution, right? So we have come to the last question. So what it is? Set current value. Set current value in STM. We have already talked. The set current means the tip, the voltage is applied between uh, tip and the surface, and we are already measuring the current. Now in constant height mode, normally, let me just yeah. So normally we are measuring in constant current mode. So we are trying to keep the current same. Now we are adjusting the height, right? So that means the voltage between tip and surface is actually maintained by the set current value. That is, we are maintaining it constant. So changing the voltage. that voltage is applied between tip and surface. That is going to maintain the set current value. And feedback mechanism is going to maintain the height, not to maintain the height, adjust the height of the tip, so that it do not get distracted or disrupt the surface as well. So that means this is not the feedback mechanism. This is the voltage applied. The voltage is applied between this and this. A bias is applied, and depending. So we are maintaining the voltage so that the constant current mode is actually there, and just height of the tip is actually changing by the feedback mechanism. So voltage is the answer, right? So here I have given all the answers that from website also you can get it. So all the 10 answers I have given, and thank you for your attention. Right. So we have discussed all the 10 questions. We have discussed all the 10 questions here. So now I'll stop here, and again I'll try right like to tell I'll like to tell you that all the videos, the previous three classes and today's class, can be like watched from the YouTube channel, my YouTube channel. And that is nothing but I'm writing it here. So the name of the YouTube channel is, so this is my name, Tanmay Khan. So this is the YouTube channel. You can go and watch the videos, previous lectures and today's lecture as well. Okay, so assignment 4 is done. So we'll meet in the next week with the assignment number 5. Right? Thank you for your attention. Okay, bye.